Deep space exploration demands materials that push the absolute limits of physics. But the exact same element that allows our most advanced spacecraft to peer across the universe permanently destroys human lung tissue on contact. Beryllium is the fourth element on the periodic table. Sitting right near the top, it is one of the lightest structural metals known to science. This chart shows the stiffness, or Young's modulus, of common structural metals. At 287 gigapascals, beryllium easily outperforms aluminum, titanium, and steel. Launching multi-billion-dollar components into orbit requires shedding every possible gram of weight. Yet those same structural components must endure immense gravitational launch forces without bending. Beryllium solves both engineering problems simultaneously. We rely on it specifically for space telescopes. The mirrors you see here maintain their exact dimensional shape even as they orbit through the extreme, wildly fluctuating temperatures of the solar system. Combining its low weight, its extreme rigidity, and absolute thermal stability makes this metal irreplaceable for aerospace engineering. But extracting these properties comes at a severe cost. Most metals bend, yield, and deform easily under pressure. Beryllium, seen here in its raw mineral state, resists traditional shaping. It behaves more like a rigid ceramic or a raw rock. Because it refuses to bend, cutting the material is incredibly difficult. Apply too much pressure with a standard machining tool, and the metal will suddenly and catastrophically fracture. Even if you manage to shape it, exposure to room temperature air causes a highly stable layer of beryllium oxide to instantly form across its surface. You cannot simply melt it down in an open atmospheric furnace. The surrounding oxygen and airborne contaminants immediately react with the metal, degrading its purity before it can even be cast. Beryllium actively resists standard manufacturing techniques. To create a single usable piece of aerospace-grade metal, engineers had to completely abandon traditional forging and invent highly specialized industrial environments. The explanation for this stubborn behavior starts at the atomic level. Beryllium atoms are incredibly small. Because the atomic radius is so tight, it creates a hyper-concentrated electrical charge density inside each atom. Unlike most metals sharing electrons in a fluid sea, beryllium's high charge density forces partial covalent bonds. These lock the atoms into fixed positions, providing diamond-like rigidity. But because they cannot slide past one another, impact from a heavy machine tool causes it to snap. Understanding this atomic stubbornness is one thing. Actually bypassing the oxygen absorption problem to mold the metal requires moving from the microscopic scale back to heavy industry. Manufacturers place the raw metal inside heavy vacuum induction furnaces. By completely stripping away atmospheric oxygen and sealing the chamber, they melt the beryllium using intense internal heat without causing any surface contamination. Overcoming the metal's microscopic atomic defenses requires extreme macroscopic force. The vacuum melting successfully yields pure aerospace-grade material, but the subsequent steps to shape it unleash a deadly byproduct. Vacuum melting provides a clean block of metal. However, milling, drilling, and grinding that pure block generates microscopic airborne dust. If a worker inhales these invisible particles, they lodge deep inside lung tissue. The human immune system detects the foreign bodies and mounts an attack, but it is completely incapable of breaking the particles down. This triggers a perpetual immune loop. The continuous aggressive attack causes severe inflammation and permanent scarring, resulting in chronic beryllium disease. Preventing this exposure requires rigorous isolation protocols. The technicians seen here assembling satellite components must wear full body protective gear and operate in negative pressure rooms equipped with advanced HEPA filtration. Capturing every single microscopic particle of dust within these facilities is treated with the exact same engineering precision as designing the spacecraft itself. The true cost of utilizing this element extends far beyond its price tag. It demands a constant, exhaustive effort to separate human biology from its microscopic fallout. With the complex manufacturing roadblocks and severe biological hazards, why does the aerospace industry continue to rely on it? Because no other element or compound in the known universe offers this specific combination. Nothing else provides the same flawless intersection of low weight, structural rigidity, and thermal stability. Our most complex deep space observatories, machines that allow humanity to map the cosmos, rely entirely on a material that is actively hostile to biology. The extreme stiffness that holds a telescope mirror perfect across millions of miles is born from the exact same atomic chemistry that snaps cutting tools and scars human lungs. It is the ultimate material paradox.